should bring Sally one day.
So we had started 7.2 a little bit last time. Remember, 7.2 was finding confidence intervals for the mean when we know the standard deviation. So the formula in 7.2, you must have the standard deviation for the population for us to be able to use the formula. So if you're not given that, we're going to explore another strategy from 7.3. Okay, so there is a way that we're going to deal with it when we don't know the population standard deviation. And I think in your project that's due next week, I think you want to do the formula from 7.3, and we'll talk about that here in a second. This is the formula that we're going to be exploring again today in today's 7.2 notes. It is for the formula for the confidence interval when we know the standard deviation. And remember that alpha, remember the alpha is your confidence level. So they're going to tell you it's a 90% confidence, and so we know that alpha would be 0.1. For 95%, alpha would be 0.05. For 99%, alpha would be 0.01. So remember, this is 0.10, this is 0.05, this is 0.01. Okay? So those are the z-scores that are associated with it. It's not a bad idea to get those z-scores in your brain. Already memorize those three. If you know those three, it's going to really help you as you go through this entire lesson and some of the stuff we're doing in Chapter 8 and I think maybe even 10. So those three numbers right there are really nice to have in your brain. Okay, so we had written that down last time. And so now let's go ahead and practice doing some stuff with it. So we had done a problem last time about the number of jobs and a confidence interval. Let's practice another one. But before that, let's think about some things. The formula, look at what we need in the formula. Let's go back to the formula for a second, and then we'll explore this slide. In the formula, we need to know the sample mean, the z-score associated with the left end and the right end. We need to know the sigma, the population standard deviation, and we need to know the number in our sample. Okay. Well, that will give us a particular confidence level, and it will give us a particular width of our interval. Okay. But the next question, ask yourself, well, what's a good sample size so that we have a certain width in the sample size? If you look, the square root of n is in that formula. It's going to really kind of affect how wide of a confidence interval we're going to have. So let's explore what they say here. Objective 2 says, well, what's the minimum sample size for finding a confidence interval for the mean so that we can get a fairly accurate estimate? So because that margin of error has the population standard deviation, it has the confidence level, it's got all of those things in it, we have to be careful of how many sample size we picked. So let's take this formula, so that's just that margin of error right here, and let's rearrange it mathematically. Let's rearrange it and solve it for n. Okay, so if we just rearrange that formula, the square root of n is down in the bottom. So if you think about what's going to happen here, okay, so let me kind of go through the process on the side here. First, we're dividing by the square root of n. So let's cross multiply it to the other side. So we would get e times the square root of n equals z of alpha divided by 2 times sigma. We still haven't gotten rid of the sigma's still there. And then mathematically speaking, we got to get rid of the e, right? Because the e is over there with the square root of n. We're trying to get n by itself. So let's divide by e. So now we get the square root of n equals, I'm just going to abbreviate it z so that we, z times sigma divided by e. Okay. And so how would we get rid of that square root in the formula? Well, we'd square both sides, right? And then when you finally square both sides, you get what you see right there. Now it's customary, because we are thinking of a sample size here, to round to the nearest whole number, right? Because we wouldn't say we want to get a sample of 2.5 people. No, you would want to actually round it to the nearest whole number. That's customary. And then we can find a sample size that does what we want. So that's the formula for sample size. Let me write it down so I got it for future reference. So we just took the formula from before and did a little algebraic rearranging, and that's what we got. So now let's look at a problem that actually does that. So it says, how large of a sample is necessary? So anytime they say, how big of a sample do we want to use that n formula to estimate the mean GPA for each undergraduate class at a large university within 0.25 at the 99% confidence level. The population standard deviation is 1.2. Now, I think the first time, anytime I've been doing these problems and practicing these problems, you really want to take out all the numbers from the problem and label what they are. So what do we know? Well, within 0.25 means that our error is plus or minus 0.25. Okay. 99% confidence. Remember, a 99% confidence means that alpha is going to be 1 minus 0.99, which is 0.01. We know the population standard deviation, so that's our sigma, is 1.2. Okay, so if you think back to our formula had a z-score associated with that alpha. We'll get to that in a second. They had the sigma. They had the margin of error. Okay. So we almost, but not quite, have everything we need. We still need the z-score that's associated with that alpha over 2. So if you look back at that chart we did, bless you, a 99% confidence interval, see how it's associated with the z-score of 258. See our z-score, 258. Okay, so, and if you looked in the chart, you would go to the middle of the chart, and you would go backwards to find the 258. Yes?
When we have a test on this, do we have to memorize all those numbers, or like that the z-score
So it is helpful to have those three numbers memorized, okay? When we take a test related to z's, which I think is going to be our next quiz, the quiz 2, this one, I'm going to give you a z-chart. So even if you forget them, you'll be able to, if you know how to use the z-chart properly, go backwards. Because there'll be some problems where they won't necessarily, they'll be using a z-score that you would need the chart anyway. So I'll make sure you have the z-chart. Okay. So now let's take these values the 0.225, the 1.2, and the 258, and let's just plop them down into the formula. So the main goal here is, yeah, you got to know the formula. 2, the other main goal is label each individual item. Because if you can label each individual item, then it's much easier then to utilize the formula. And then we plop the things in. See, then here's where you just put them in. So it's 2.58 times 1.2 over 0.25, and that value is going to be squared. Now you get this, 153.36, and so on and so on. This is the number of people we want to sample. These are people. So we would round that to the nearest whole number, and we would get 150. Well, they always round up. Think about this. Why? I guess we should always not round. Any decimal value at all chunked off the end should go up 1, and this is why. If we wanted to take a sample of 153, even though it rounds using your 5-point rule to 153, it would not be helpful, right? We wouldn't get the amount we wanted because that 0.3653456, we need one more person to sample to make it at least what we want. So for these ones, round to not the nearest whole, round up a whole. So unless it comes out to be an exact whole number value, which they're probably not going to. So just round them up for these particular ones. It's like, if you can't want a half of a bunny rabbit, you're gonna say, well, hey, I'm just gonna need another bunny rabbit. You don't want a half of one. Okay, so that's all 7.2 is. It's either finding the confidence interval or finding what sample size will give you that confidence interval. 7.3 is how do we find a confidence interval of the mean when we don't know the population standard deviation. We don't know the sigma. Because many times we might not have that information. So we want another route to take. Like, what else can we do in order for us to find the confidence interval that we want? So that's what 7.3 is about. Okay. So, most of the time, if the sigma, the population standard deviation is unknown, we can use the sample standard deviation as an estimate. So we're going to need to rely on our sample. And we can just find the standard deviation using our sample standard deviation formula. Now there's lots of standard deviation calculators out there. Usually you can tell it whether it's a sample or a population standard deviation, and they'll tell you sometimes both. And so make sure that you use the sample standard deviation when it's appropriate. When S is used, especially when the sample size is small, critical values greater than the Z alpha over 2 are used in confidence intervals in order to keep the interval at any given level. We're going to use something called a T distribution, sometimes called a student T distribution. The T distribution allows for the fact that we're using a sample standard deviation. The higher the level, the number of samples we take, the better. Sometimes we want it to be a normal distribution. for the t distribution to be accurate. Now, just like in the back of our textbook, there is a z-chart, and if you go online and you look up a z-calculator or a z-score calculator, there's also in the back of your book a t-score or a t-chart, a t-distribution chart, and there's also t-score calculators or t-distribution calculators online. And so you can find them pretty quickly if you just go online and search for a t-distribution calculator. Just put the word calculator behind everything. Standard deviation calculator, t-score calculator, z-score calculator. You're going to find all these different calculators online. And then if you explore some of the formula options in Excel, if you have the most up-to-date Excel, there are some statistical things you can find right in there as well. And we'll probably, I think we're going to have some time. If it's not next week, then the week after, we're going to probably have some time to pull up Excel and play with some of these things one more time. And I'll probably send you a document that we can all open up and look at. So let's look at how the formula, I think that's what's next. Yep. So after we go through here, some assumptions we have to make about the t-distribution and what it tells us, I'm going to give you a formula. So first, they must be random samples. We can't just take samples without following the rules that make us take our random samples. And here's where we have to have the samples must be normally or approximately normally distributed. If we're not told that, then we must have a sample size of 30 or more. So sometimes they will, in a problem, they might say, we don't know the standard deviation. Our sample size is normally distributed, go. Our sample size is 20, but it's not normally distributed, so then we couldn't go. We couldn't use this t-distribution without having those facts. So they're always going to mention, hey, it's normally distributed, or if they don't say it's normally distributed, you'll know that the sample size might be 50, 100, 200, or something like that. So it's important that you realize t-distribution is when our standard deviation is unknown, the samples are random, and we should have a normal distribution unless we have a sample size bigger than 30. Just like any normal distribution, our t-distribution should be bell-shaped. And if it's bell-shaped, number 2 just goes with that. It's symmetric. Because of that symmetry, we get t-scores that are above and below the mean, just like we had z-scores that are above and below the mean. And, we get those tails that are the same shape on both sides. And, we get lots of things because of the fact that it is symmetric. The mean, median, and mode are all equal to 0 and are in the center of the distribution because of the fact that it is a symmetric distribution. They got to fall smack dab in the middle. And then we're going to assume these things. If they give us the information and they'll say, hey, it's normally distributed, we don't know the population standard deviation, do the problem. And you can assume then that you can use a t-distribution. The curve keeps going out. Those tails keep going out. So, if you were to draw your distribution, those tails keep going forever and ever and ever. They just get closer and closer to 0. But they never actually touch the x-axis. You get real, real close. The standard deviation is greater than 1. Remember, our standard normal distribution has a 0 mean and a standard deviation of 1. In a t-distribution, our standard deviation is bigger than 1. The t-distribution is based on something called the degrees of freedom. Degrees of freedom are really just related to how many people, or how many things, how many samples you took. The higher the number of samples you take are, the more our t-distribution will look like the standard normal distribution. Oh, that's what the next thing says. As the sample size increases, the t-distribution approaches the standard normal distribution. So here's a little picture that kind of depicts that degrees of freedom. So the z-curve, our standard normal distribution, is that black one. And the first one, that's the lowest one, only has a t-score for degrees of freedom of 5. And the t-distribution for degrees of freedom of 20, look how it starts to get closer and closer to being an actual z-curve. Now, what the degree of freedoms are, it's the number of values that are free to vary after a sample statistic has been computed. Now, the best way to remember it is it's just the number that you sampled minus 1. So it's just subtract 1 from the sample size. They usually just abbreviate it DF, and it's just the number I've sampled minus 1. That's all it is. So if you have sampled 20 people, your degrees of freedom would be 19. And when you use the T chart in the back of your book, you would look for the degrees of freedom of 19. And that's the column you would use, or the row that you would use. So if you have your book, flip to the back. We're going to take a second and we're going to look at the T chart, the T distribution chart, and we're going to just make sure we understand how to use it. There are T-score calculators. Let me see if I can find one I can show you. I found that this website here, I'm going to point out, it's social science statistics calculators. Here, I'll kind of show you real quick. This website here has every type of calculator that you want. So it's just a nice, I found the Z chart, I found T-scores, I found all kinds of stuff. So there's lots of tools out on the internet that you can find. I just typed in T-test calculator, and you can find it, okay? Okay, so let's look at our Z chart. So if you have the text, look in the back of the book to table F. So I just kind of chopped off a top of the chart so we can just kind of analyze what it means. So along the side here are the degrees of freedom. So if we only sampled 2 people, we would use the first row because our degrees of freedom is 1 less than how many people were sampled. If we sampled 8 people, we would use the degrees of freedom as 7. We would use that row. Okay. Now let's assume that our number of people was 8. And so let's focus on this 7 row here. And it's kind of hard to see, but look at what we got. Now we're going to explore of one-tailed test versus a two-tailed test as we go through some of the samples. But look at what we see here. So if we have an 80% confidence and our one tail has an alpha of 0.10, we would use 1.45. But if we wanted a two-tailed test and alpha is 0.10, we would use 1.895. So it's important that we know how many tails we have. And we discussed that in other sections. If we have a less than or a greater than only, then it will be a one-tailed test. If it is not equal to, so it's a greater than and a less than test, or they say the words two tails, then it's a two-tailed test. But we'll explore that as we go.
Wouldn't the 80% have to go with the 20 if it's a two-tail and the 10?
Say that again?
Since it's 80% confidence, if it's a two-tail, wouldn't it have to be 0.20, like 20%?
It depends on, okay, so remember how and we're going to explore this in the formula here in a second. Remember how our z-score, we did alpha divided by 2? Mm-hmm. In one tail, you just look at the one tail has to be half the half score, but the two tails is the original alpha.
So two tails is just the regular alpha?
Yes. And one tail is going to be half of that. And I'll explore it when we get to it a little bit more. Yeah. And I don't think this one says anything. Oh, okay. So get your book open if you have it, if you brought it with you. We're going to just find the different z-scores in the book. So in this example, we're going to find the t-score, but see how it says alpha divided by 2. Okay. We're going to find the t alpha divided by 2 value for a 95% confidence interval for a sample size of 25. Okay. So first thing you want to discover, you want to think to yourself, is okay, my degrees of freedom is going to be 25 take away 1, or 24. So that tells me that I want to use the row with 24, right? Okay. Now, it says that we want to find alpha divided by 2. So for a 95% confidence interval, mine's covered up a little bit, but here, let me pull it back down so you can see it. For a 24, and if you go to the top, so 95% is an alpha of 0.05, right? And a alpha divided by 2 is 0.025. And see how here it says one tail, 0.025. So that tells you what we're going to use. 2.064. Okay, see, the reason we know it's alpha over 2 is because that's what they physically told us. Now we're going to have other markers in the problem eventually that we'll know it's an alpha divided by 2. Okay, we'll know that as we go. Okay, so let's just go over that one more time. The degrees of freedom is 1 less than the sample size, so that's why we use the 24 row. Our confidence interval, just take 95% from one whole, which leaves you 5% or 0.05. But we want alpha divided by 2, so then that's going to be that 0.05 divided by 2, 0.025. And that's why we're using this column. And so it's 2.064. And if you look at the chart, you'll do that. And we'll practice it as we go through the problems. Because as soon as you throw, you know how when you throw words in.
So if it were,
Yeah.
So if it were 2 tails, you would use the 0.05, but would it go 1 column to the right?
Yes. Wait.
Because that's what
Yes.
we did on the last example.
Yes. Yes. And I'll verify that when we go through the next problem. But yeah, I'm pretty sure that's what we have to do. Most of these time, because most of these problems, we are making a interval. So we use 2 tails. That's customary when we're making a confidence interval. But eventually we're going to do some hypothesis testing in Chapter 8, where we do have a 1 tail versus a 2 tail. And that's, I think, when it comes up a little bit more. Most of these are 2 tails.
What do you mean go to the next column?
If you take, and you're only using 1 tail, you have to think about the 0.05 as it is instead of a 0.025. Don't worry about it yet. You'll see it more when we get to the next section. For now, we're using 2 tails. We're using the 0.025.
Wait, I thought we were just using 1 tail. I'm confusing myself now.
Okay, stop. All that we were looking for now, don't worry about whether it's 1 tail or 2 tails right now. All we have to look for is the fact that an alpha over 2 automatically is 1 tail. So if they say that notation means 1 tail.
Well, see down here at the bottom of the t-distribution, it has 2 tails, alpha over 2.
Because it's going to end up being an interval, we're going to use plus or minus. When we actually go to do a problem, we're going to use plus or minus t of alpha over 2. You'll see when we get to a problem. It's hard to describe
I
otherwise.
was just thinking alpha over 2, the 2 and 2 tails.
It does, yes.
Okay.
Think that. Keep thinking that.
Okay.
Yeah. And you'll see where it'll change up a little bit in chapter, I think it might be in chapter 8, if not for sure by chapter 10. When we do some t-score stuff where we're doing hypothesis testing, but we'll practice that when we have to. Yeah. Because look at the formula. See what's in it? Alpha over 2. Now stop and look at that formula and let's compare it to the one I wrote on the board. What's the z-score replaced with? The t-score. Okay? Because we don't know the standard, the population standard deviation. What was the population standard deviation replaced with? The sample standard deviation. And everything else about that formula is exactly the same, except now we're relying on a t-score and not a z-score. That's the only difference, is here's a t-score. There's a t-score instead, and there's an s. But what is an s? S is a standard deviation. It's just the sample standard deviation. So the formulas are pretty close, but one, unfortunately, we just don't have the real standard deviation. We can only rely upon our sample. So you only really use this if we don't know the standard deviation for the entire population. You want to use a z-score if you can. because it will be, I guess, more accurate in a way that you can think about it. The t-score is a rougher estimate. But it's really kind of the same formula adjusted because we don't know the sigma. We don't know the population standard deviation.
Where does the degree of freedom come into play?
That's the degrees of freedom will come into play in which column of the chart you use.
Okay.
So along that left side or which row of the chart you're going to use. So along that leftmost column, you would find your degrees of freedom, and that's where you go over and use your.
Have to deal with the formula and all that stuff.
And if you look within a column, the values don't change a whole heck of a lot. They get closer and closer to those Z numbers the higher you go down the chart, because our t-score and our z-score will get closer and closer the more we have in our population or in our sample. So the best way to describe this is to look at an example. There's no two ways about it. And then I can show you where to look on the chart, and we can practice all that together. So we can think about this right now as like a two-tail because of the fact we're minus in it and plus in it. We're on both sides of the sample or of the mean. Okay. So let's look at an actual example. So it says the number of students who belong to the dance company in each of several randomly selected small universities is shown here. Estimate the true population mean size of a university dance company with a 99% confidence. The data is listed below. Okay. So we've got this data, and they ask us to do this test. Well, the first thing we have to do is find the sample mean and standard deviation for the given sample. Now, if I were to do it, which I think I might have done for this problem, I took all those numbers, I put them in a standard deviation calculator online, I entered them in the list, it calculated the mean, it calculated the standard deviation. Okay, so you can just list them out. They'll do that for you. If I'm going to give you something like this on a quiz or a test, it will be a very manageable number. It wouldn't even be as many as this in the actual data, because I want you to be able to do it by hand. I don't want us to have to rely. So the only time you're going to be doing something like this would be if it's an assignment or something that you can use technology. Okay, so I did the technology, and I found, using some type of standard deviation calculator, that the sample mean was 29.8, and the sample standard deviation is 6.18. Now, before we go further, because that's our first step, did they tell us sigma? Did they tell us the population standard deviation? Did they ever mention it in the problem? No. So that is our unknown.
But did we just find the sample?
That's the sample.
Okay.
That's the sample standard deviation, not the population standard deviation. Remember, they only picked 19 universities, but that's just a sample of all the universities. And so our sigma is unknown. That should immediately red flag us, hey, I've got to do a t-test. So that's the difference compared to a problem we did last week. That one, they gave us the population standard deviation. Here we don't know sigma. So now we know we have to do a t-test. So what do we have to do a t-test? Well, there's some things we need to know. We need to know the degrees of freedom. They sampled 19 universities, so 19 minus 1 is 18. So the degrees of freedom in our problem is 18. We have a 99% confidence interval, so our alpha is 0.01. So we need our alpha divided by 2 number, which is 0.05, 0.005. Okay. So we've got to find the t-score from the table. We're going to find the row that says degrees of freedom 18. We're going to go over, and we're going to find the t-score, and the t-score is 2.878. Okay, so make sure, if you got your book, take a look at it. Make sure that you're getting the same score that you see there. Okay, so we would go over on row 18, degrees of freedom 18, go over till we find the alpha over 2 we want, which is 0.005, and then we find the 2.878. Okay, everybody see that part? Okay, so now we just plop it into the formula, right? That is what's going to be added and subtracted from the sample mean. Okay, so that's that 2.878 times our standard deviation of the sample, 6.18, divided by the square root of 19. We get this number. I didn't round it too much until, you can round it later on based upon how many decimal places. Now remember, the original data is whole numbers, so 1 decimal place is fine. If you want to go to 1 decimal place, that's fine by me. And then we add it and we subtract it from the sample mean to find our confidence interval. So we add it to give us 33.88. We subtract it to give us 25.72. Now if you look, here, let me scooch that down. If you look, the way that you would write this is our mean is somewhere between 25.72 and 33.88. With a 99% confidence, we can say that the mean is somewhere in that interval. Make sense? Kind of, maybe. Okay. Now, we need to do one more. For a random sample of 24 operating rooms, they are looking at the mean noise level. And in the study, they found that the mean noise level in those rooms was 41.6 decibels. The standard deviation was 7.5 decibels. Find with a 95% confidence what the 95% confidence interval of the mean would be in the operating rooms. So before you jump in and do the problem, let's label everything we got. Okay. We know the sample size is 24. We know the sample mean is 41.6. We know the sample standard deviation is 7.5. We do not know that. We know our alpha is 0.05, so our alpha over 2 is 0.025. Okay? So first you're just kind of labeling what you know. I think it's a good idea before you even jump and try to solve the problem, label every single number that's in that problem. What did they tell me, so what do I need to do? Okay. Second step, what are your degrees of freedom? Well, there were 24 sampled, so just go 1 less than that. The t-score, so we're looking at a t-score of alpha over 2 when our alpha over 2 is 0.025. So I guess we could write it like this. And if you look on the chart, that's 2.069. Okay. Now I would calculate the actual t-score times s over the square root of n. I would just do that so then I can add and subtract it from the sample mean. And so when you do that, I just plop those numbers in, 2.069 times 7.5 divided by the square root of 24. And I got 3.17. Now remember, that's what we are going to add and subtract from the original sample mean to find our confidence interval. So here's where you subtract it. That's your lower bound and that's your upper bound. So we can say with a 95% confidence interval that the mean, the true mean, is somewhere between 38.43 and 44.77. So the t-test and the z-test for confidence intervals are exceptionally similar, except one you know the standard deviation for the entire population, one you don't. So you just have to use a slightly different value, different chart for one compared to the other. And I'm pretty sure for the homework I was able to use the charts every single time. You can use some of the calculators are online, but I think there's only one I had to list out all the numbers to find the sample standard deviation and sample mean. I think most of the time I was able to just do it by hand and it wasn't a real long process. Okay, so the things you want to ask yourself when you're going to do these problems: is sigma known or unknown? Okay. If you say yes, then it's a z-score. It's a z-score, a z-value that you want to find. If you say no, then you have to ask yourself, can I use the t-score? If you use the t-score, remember, if the sample size is bigger than 30, you can use the t-score. No worries. But if they give you a sample size less than 30, you better make sure they've said in the problem, this is normally distributed. They'll say that. And almost all of these, they've said it. But just, it's something to make sure that you look at it and you go, is it following the rules that make me be able to use a t-score or a z-score as to which one you use?
You had me all worried. I was like, oh, there's so many more slides.
I know. The homework for Chapter 7, let's talk about that real quick. There are 6 problems from the review exercises, and then you need to jump to the chapter quiz that's a few pages after that. And there are 11 problems, but they're just, like, a lot of them are more true, false. I think even a few multiple choice from those 11. And that is not due until the 29th. So that is your homework number 7. So there you go. There's the rest of Chapter 7.